Hello everyone. So let's continue our study on this three-phase systems, and this time I'm going to talk about unbalance in a three-phase network. So unbalance is a situation, as you know, when everything is not symmetrical with all three phases. So sometimes the load can be unbalanced and the supply is balanced, and sometimes the supply can be unbalanced and the load is balanced, and sometimes both can be unbalanced. So, how to analyze the circuits in such a situation? Just through one or two examples, I would like to present in this video. So, just in this series, in the last video, we had seen a case of a balanced delta delta system. So, I would like to start with that. So, imagine this. So, we have a source which is balanced, and we also have a load which is balanced. So, to begin with, and later I'll make it unbalanced. The source is like this. So this is a delta connected three-phase voltage source. Let's call this point A, B, and C. And the load is also like this. So this box represents some kind of impedance. So I'll use the same numbers that we have been using in this series. So 2 plus J7 ohms, 2 plus J7 ohms, and 2 plus J7. So basically this is again a three-phase delta load which is balanced. I'm just connecting the respective, so this is B, A and C. So I named it such that B is connected to B. So here what I'll do is I'll introduce a switch. So I'll come back to this switch later. So this is what is the source of unbalance in our circuit. So this is 100 volts, 0 degrees. So let's give a notation. Let's say this is VA and this is VB. 100 volts minus 120 degrees, and this is VC minus 240 degrees. So this side is plus, this side is minus. I can also mark the currents. So these are line quantities IA, IB, and IC. Let's mark the voltages and currents in the load also. So let's call this IAL. IAL is the load current in the A phase. So this, for our purpose, this is considered as A phase, and this one let's consider it as a B phase. IBL is the B phase load current, and then let's consider this as a ICL. This is a C phase current of the load. Now similarly, let's call this as IAS, A phase source current, and let's call this as IBS, and let's call this as ICS. So if this switch was closed, we have already solved this problem in the previous video of this, which is a balanced delta source connected to balanced delta load. Now if I open this switch, what happens? So what will be the value of IA, what will be the value of IB, IC, what will be the currents in the load, what will be the voltages in the load and in the source. Of course, the source voltages are known. What are the currents in the source and so on. So this is a simple unbalanced network because of the switch here. The switch could have been in B line or switch could have also been in A line. So it is basically symmetrical in that way. Now the switch can be here also in this between B to C. The switch can be between A to C. There are several cases, several ways we can make a balanced system into unbalanced system. But for this time being, let's go with this. So immediately I can write IC equal to 0. The current in the line C will be 0 because the switch is open. So there is no current in this line. And analyzing the circuits like this, or in analyzing in general any circuits, you can also think of a concept of super node. So what is a super node? So you understand a general node, like a simple node. A is a node, B is a node, and C is a node, as you can see here. And then at that node you can apply Kirchhoff's current law and so on. But if I draw a line like this, if I take a part of the circuit and then consider it as a supernode, then the KCL also applies there. The currents entering into the supernode will be equal to the total currents exiting the supernode. So IA is entering into the node. Whatever happens inside, we don't care. IB is also entering, but IC, it's not, IC is 0, we already established that. So therefore, IB plus IA will be 0. So that is KCL for supernode. So KCL for supernode. Supernode is nothing but just a name for multiple nodes combined into a small part of the circuit. So here I can write IA plus IB equal to 0 or IA equal to minus IB. So whatever IA value is there, so it will be the magnitude will be same, the angle will be, or the phase angle will be moved by 180 degrees. That is the meaning of minus. So let's come back here and then see. It is very easy to analyze. I can right away tell what is IAL. So this current, because this voltage is 100 angle 0, I can just calculate what is IAL. So IAL is nothing but VA by ZA. So that is nothing but 100 angle 0 degrees divided by 2 plus J7 ohms. So here I'll get some current. We'll do that calculation shortly. So once I know IA, notice that if this is open, these two get series connection and also has the same voltage. The voltage is exactly same VA that is appearing between these 2 points AB. So I can also find the IBL and ICL. So IBL will be equal to ICL because this current is 0. So here the current is 0 amperes. So these two currents are equal. So IBL will be equal to ICL, which will be equal to half of, see, because this side is positive, VA is positive and VB is negative, so the current direction should be like this, but because these two are here like this and these two are in series, 2 plus J7 in series with 2 plus J7, so I can write minus of VA divided by 2 plus J7 plus 2 plus J7, basically half of the current. So it's like a simple parallel circuit now. So once I get IAL, IBL and ICL, what I can do, so IAL and ICL through that, or I can find IB through this, IAL and IBL, IAL minus IBL, through KCL at node B I can find IB, then I can find IA. IC is already there. So let's do that now. Let's solve for IA1. So I switch over to my MATLAB interface. What you see here is for the previous problem. So let's clear everything, or not everything actually. So let's clear up to here. So what we have here on the left is the code. So VA value is 100 volts and VB is 100 volts with a phase angle of minus 2 pi by 3, that is minus 120 degrees. VC is defined as a voltage of 100 volts with a phase angle of minus 4 pi by 3, or that is minus 240 degrees. And I am gathering VA, VB, VC into a vector called VABC. Now, what is IAL? Just now we calculated, that is we written down VA divided by 2 plus I7. So this will tell me what is IA1. Now what is IB1? IB1 is nothing but negative of VA and divided by 2 plus I7 plus 2 plus I7. So because these two impedances are in series, so they will add and then finally divide, and then minus sign also, you understand. ICL is also equal to it's also equal to IBL, because as we have explained from the circuit diagram shortly. So this is calculation of unbalanced load currents. So let's see what they are. So if I run this, I think I should do 7 into I, or I into 7. or I think 7I will also work. So this is IBL. So on the right hand side now we got the solution. So IA1 is this, IB1 is this, and IC1 is this. So as noticed, uh, they are half of each other. So IB1 is half of IA1 and so on. So let's calculate the magnitudes and angles. So IABL, ABCL, I'll just combine them into a vector. IAL, IBL, and ICL. This is combined into a vector. And then I want to display the magnitude. Therefore, I'll say absolute value of IABCL, and then I want to display the angle of IABCL. So angle will be in radians, so I multiply this factor of 180 by pi to convert the radians into degrees. Again, some syntax error. So the closing bracket is missing here. Let's do more debugging. So I'll comment this line and then let me just execute up to here. Okay, so three currents are being formed. So I think the problem is in line 15, IABCL. Okay, so this closing bracket was a problem. So here the bracket should be square bracket. Yeah. So now I'm getting the currents. So 13.73 angle minus 75 and then 6.86 and angle 106. So these are my phase currents. So let me write it down. So IAL, IBL and ICL. So these are the load phase currents. That is 13.73, 6.86, 6.86. Whereas this angle is minus 74 degrees. This is exactly same as what we had seen before, and 106 degrees and 106 degrees. So these two are exactly same. Now, what about the line currents? These are load currents, load phase currents. So what about the line currents? So if I go back here, what is IB? IB is incoming current, which is nothing but outgoing current. So I'll write KCL at node B. KCL at B. Incoming currents are positive, so IB plus IAL is equal to IBL. IB plus IAL equal to IBL. So these are incoming currents, this is outgoing currents, so they are equal. So IB will be equal to IBL minus IAL. I can right away calculate that. So I capital B is IAL minus IBL. So I'm getting the current here 5.66 minus 19.8. So I can again display the absolute value of IB, and I can display the angle of IB. 20 and 20.6 and minus 74 degrees. So once I get IB, IA is nothing but minus of IB. So this is nothing but minus of 20.6 minus 74 degrees, or 20.6, and then I can add 180 degrees to it. So 180 minus 74, how much will it be? 180 minus 74 will be 106. Yeah. So here 106 degrees. So this is my IA current. So I had, and IC anyway, we started off by saying IC is 0 because the switch is open there. So once I get IA, IB and IC, the next step would be to calculate IAS, IBS and ICS. The source side currents. So remember, although the voltage is balanced, the currents are unbalanced because they are not equal. IA value is different, IB value is different, and IC value is different, the magnitude, even the angles. Okay, so let me write it in matrix form. IA, IB and IC. So this is 20.6, 106 degrees. This is 20.6 minus 74 degrees and then 0. So this is my line currents. Let's do phase currents of source. So look at the source. I know IA and IB and IC. So what is the best way to find IAS, IBS and ICS? So one thing you can notice right away here is IC is 0, so therefore there is no current on this branch. So ICS will be equal to IBS. So that is one thing we can write down here. ICS will be equal to IBS. The C phase source current will be equal to the B phase source current. And how do we calculate further? IAS. So basically one thing we should know is that if I look at the source, it is like a voltage. So VA, VB and VC are here. So let me redraw the source. I just take only two bus bars. This is VA 100 angle 0 degrees. This is plus minus, and this point is A according to our diagram, and this point is B. So you can just notice it here again. This point is A, this point is B. And point C is in between, and in between there are two voltage sources, VB and VC. So this is voltage source VC and this is voltage source VB. And the direction is like this. This is 100 angle minus 120 degrees, 100 angle minus 240 degrees. And one thing you should know by now, this point is C by the way, so we are not interested about that point now. And this current going out is 20.6 angle 106. This is IA. So the current which is coming back, IA minus IA, or I can put IA with reverse sign, will be same, or actually we are using IB here. It will be exactly same, but in the opposite direction. Now you notice that this branch, if I add VB and VC and then reverse it, I'm sorry, this should be plus and this should be minus. These two voltages are exactly same. So what happens is that they end up sharing the same current. So in other words, what I'm saying is VA is nothing but minus of VB plus VC. If you see here, in fact you can check this, you know all these three values. So if you check this, let's check it actually. So if I already calculated VA, VB and VC. So first I'll display what is the value of VA, then I'll display what is the value of minus of VB plus VC. And you will notice that both of them are 100. So let me run it. So on the screen you can see 100 and then this is also 100 and 4.2 e to the power of minus 14. So this the imaginary component is not there almost. So both are equal actually. So we have two parallel paths with same voltage, so they will share the current in the same uh, value. So therefore the current here, this current is IAS and this current is, in fact the current will be reversed now, ICS and IBS. These two are equal and this IAS will be half of the IA. So that is what we learned from this, because these two voltages are same. There are other ways to calculate this, but then I thought this is more conceptually interesting way to solve. So from this is since VA is equal to this, from circuit above, IA in source is nothing but I line current by 2. So which is nothing but 20.6 by 2, angle remains the same, which is 106 degrees. 10.3, 106 degrees. This is A phase source current. What is B phase source current? This is nothing but minus of IAS, which is minus of 10.3 angle 106 degrees. This is nothing but 10.3 angle 74 degrees. Minus 74 degrees, sorry. So just 180 degrees phase shift, which is also equal to ICS. So now I can find out what is the A phase power. What is the B phase power supplied? What is the C phase power supplied? So this is nothing but IAS VA, sorry, VA into IAS conjugate, VB into IBS conjugate, VC into ICS conjugate. So this way I'll get the three powers. Similarly, I can also calculate A phase power received. Similarly, B phase power received, C phase power received. So this will be again VA, or I can use the impedance. So IAS into Z into IAS conjugate. This is L. IBL into Z into IBL conjugate. ICL into Z into ICL conjugate. So this is the formula for load power. So I can always check, which phase power is going to which phase and so on. So this is how you analyze the unbalanced circuit. So let's do that. So I go back here. So IAS is nothing but IA divided by 2. IBS is nothing but minus of IAS. ICS is nothing but IBS itself. So I hope you are now following the simple thing. This is not not very difficult actually. It's straightforward. So IA was not defined. So IA equal to minus of IB. So you can see on the right hand side, you can see all the three currents, IAs, IBs and ICS. So let's look at the powers. So this is calculation of source currents. So by the way, these three are IA, B, C, S. I'll just combine them. IAS, IBS, ICS, and then I'll just display the absolute value of IABCS and then angle of IABCS into 180 by pi to convert to degrees. So you notice this is exactly what we had written. The source current of A phase, B phase and C phase 10.3, 10.3, 10.3 and then these are the currents. So this is what I have written here. 10.3, 10.3 and so on. So it's exactly matching with our hand calculation. Okay, so let's do the calculation of powers. Source phase powers. PA source, PB source. Power means I'm talking about the complex power. In fact, I'll call it SB source. Sorry, SC source. So what is this? VA conjugate of IAS. This is BS and this is CS. So again, this is a very simple formula I'm just writing for calculating of complex powers. These are from the source. What about complex powers from the load? So let's replace all this by L, this by L, this by L, and we have also calculated the load currents. So conjugate of IAL and then IAL into 2 plus 7i. This is a load element. So this term I will copy it for the other cases. So this is BL and this is CL. So same thing what I have written on my blackboard, the same formulas I am entering into the MATLAB code here. I just execute it. So here I get all the solutions. So let me paste it here. Okay. So you notice that the total power supplied and total power consumed, the power balance should be maintained. But apparently it's not being maintained here. 283, 999 and this. For now I'll just leave it for you to check it, and then if you have these things actually should tally. The total power supplied by the source should match the total power consumed by the load. So somewhere I made a mistake. So it's fine. It's not that everything should be correct all the time. So I leave it to you to check this once again, and then uh, please leave your comments where I made a mistake. These powers are not matching uh, according to me. So let's see where it is not matching. The total power supplied should be equal to the total power received by the load. So both active and reactive powers. So try to sort it out. But then in this video, I've just shown how to analyze an unbalanced case where the switch is open here, and then I'm just applying my traditional network analysis methods to find out. Okay, thank you.